A faint pyramid of ghostly light sometimes rises from a dark horizon. This is the zodiacal light, a cosmic whisper that has puzzled sky watchers for centuries. By the end of this story, you will understand the grand detective hunt to solve one of our solar system's oldest and most beautiful mysteries. We will follow the clues from ancient astronomers to cutting-edge space probes, investigating where this ethereal dust comes from and why its very existence defies explanation. What force could possibly be sprinkling countless tons of fine powder throughout the inner solar system, creating a permanent, glowing fog around our sun? The answer is closer than ever, yet it remains just out of reach. What does it feel like to witness a genuine astronomical mystery with your own eyes? This pyramid of light is not a trick of the eyes, but a real structure in space. To understand it, picture our solar system not as a collection of empty orbits, but as a vast, dusty room. The zodiacal light is the glow you see when the sun, hidden just below the horizon, shines its flashlight through that room. It illuminates countless trillions of dust particles, each one smaller than a grain of sand, that float in a colossal, flattened cloud stretching from the sun out past the orbit of Mars. This is not a solid disk, but a permanent, tenuous fog of cosmic powder. Astronomers call it the zodiacal cloud, and it is our solar system's most prominent feature after the sun itself. For a stargazer, seeing it is like catching a glimpse of the skeleton of our planetary neighborhood, a faint outline of the plane where all the worlds go around. The light itself is incredibly subtle. It appears as a soft, cone-shaped glow, widest near the horizon and tapering upward along the path of the zodiac constellations, which is how it got its name. It is often described as a false dawn or a lingering twilight, but it is something far more permanent. You need perfect conditions to see it, a night with no moon, far from any city lights, with exceptionally clear and transparent air. The best times are in the spring, just after evening twilight completely fades, or in the autumn, just before morning twilight begins. When you finally spot it, rising like a pale, ethereal pyramid from a truly dark horizon, the experience is unforgettable. It feels less like observing an object and more like perceiving a dimension of space itself, a gentle reminder that the void between planets is not empty at all, but filled with a slow, silent snow of stardust. That gentle pyramid of light has been a companion to humanity for far longer than our telescopes. The earliest clear records we have come from brilliant Islamic astronomers of the medieval period. Around the year 1000, the Persian scholar al-Biruni described this glow with remarkable accuracy, noting its position along the zodiac and its seasonal appearances. In the West, it remained a puzzle, often mistaken for a faint extension of the Milky Way or some strange atmospheric effect. It was not until the 1600s that the Englishman Joshua Childrey made a crucial observation, correctly linking the glow to sunlight, though he still thought it was a vapor in our own atmosphere. The real breakthrough arrived with the keen mind of Giovanni Cassini in the 1680s. Famous for his studies of Saturn, Cassini looked at the evidence and proposed a radical idea. He suggested this light was not of our world at all, but was sunlight scattering off a cloud of tiny particles orbiting the sun itself, a sea of interplanetary dust. This was the first scientific step toward solving the mystery, shifting the cause from Earth's sky to the space between planets. Culturally, this glow has always held a quiet power. In Arabic, it is known as al-Fajr al-Kadhib, the false dawn, a term woven into poetry and lore, describing that moment when a faint light promises morning but the true sun remains below the horizon. One can easily imagine ancient sky watchers, from desert nomads to early farmers, seeing this persistent glow and weaving it into their understanding of the cosmos, their rituals, and their stories. It was a permanent, gentle mystery in the heavens, waiting centuries for its true nature to be revealed. Cassini's brilliant hunch was correct, but it only identified the culprit, not its origin. The source of that ethereal glow is a sea of unimaginably fine powder. These are interplanetary dust particles, the smallest and most numerous solid objects in our solar system. To grasp their scale, think of the finest dust you see floating in a sunbeam in a quiet room. Now shrink those motes down 100 times more. Most are smaller than the width of a human hair, mere specks ranging from the size of a bacterium up to perhaps a grain of sand. A few might be as large as a millimeter, but these are the giants in this microscopic realm. They do not float alone. Trillions upon trillions of them form a permanent, tenuous fog, a cloud so vast it boggles the mind. This is not a random scattering. The cloud is shaped like a colossal lens or a flattened disk centered perfectly on the Sun and aligned with the plane of the planets. Earth, along with Mercury, Venus, and Mars, orbits entirely within this dusty disk. We are swimming through a cosmic snow globe, one illuminated from within by our star. So where does all this dust come from? The leading suspects are two familiar processes. The first is comets. As these icy wanderers swing close to the Sun, their frozen gases heat up and erupt into space in magnificent tails. This process, called sublimation, does not just release gas, it also liberates countless dust grains trapped within the comet's icy matrix. Each comet passage is like a giant pinata being cracked open, scattering a fresh stream of microscopic debris along its orbital path. The second major source is the asteroid belt. Out between Mars and Jupiter, millions of asteroids are in a constant, slow-motion dance. Occasionally, they collide. These impacts are not giant, catastrophic explosions, but more often gentle nudges and crunches that grind rock against rock, producing clouds of fine powder that gradually drift inward toward the Sun. This dust is the very stuff of creation. Its composition is a pristine record of the early solar system. Scientists analyzing particles collected high in our atmosphere have found they are a mix of silicates, which are rocky minerals, carbonaceous materials rich in carbon, and tiny remnants of ices. They are, in essence, the leftover building blocks that never coalesced into planets, the primordial rubble of our cosmic neighborhood. So the beautiful pyramid of light you might see on a perfect night is in truth the gentle glow of ancient history, the illuminated dust of comets long gone and asteroids that collided before human civilization began. But the pyramid of light is only one piece of a much larger structure. If you could see with the eyes of an owl on the darkest night, you would witness the full, breathtaking architecture of our dusty solar system. Directly opposite the Sun, at the antisolar point in the midnight sky, lies another ghostly patch of light known as the Gegenschein. This German word translates to counterglow, and it is an apt description. While the zodiacal light is forward scattered sunlight, seen when we look toward the Sun, the Gegenschein is sunlight bouncing directly back toward us, like car headlights illuminating a distant fog bank. It appears as a very faint, oval-shaped patch of luminosity, so subtle that it is often described as an absence of darkness rather than a true glow. It is the ultimate challenge for amateur astronomers, requiring the most pristine skies on Earth to even have a chance of glimpsing. And connecting these two luminous cones and this central patch is the most elusive feature of all, the zodiacal band. Imagine a complete, impossibly faint ring of light tracing the entire path of the zodiac constellations around the sky. This band is the bridge. It is the continuous, tenuous glow of the interplanetary dust cloud, visible as a seamless pathway linking the evening zodiacal light, arching over the midnight Gegenschein and flowing down into the morning zodiacal light. When visualized together, these three features create a complete, glowing framework in the heavens. They are not separate phenomena, but different perspectives on the same colossal object, a single, lens-shaped cloud of dust centered on the Sun, with Earth embedded within it. This celestial skeleton, traced in the faintest possible light, reveals the true scale of our home system. It shows us that the planets orbit within a permanent, structured haze, a gentle fog of ancient history that paints the entire plane of our solar system with a brush of ethereal luminosity. This elegant celestial skeleton, however, hides a glaring mathematical contradiction. For decades, astronomers have been trying to balance a cosmic checkbook, and the numbers simply do not add up. This is the heart of the zodiacal light mystery, a problem scientists call the dust budget. Imagine trying to maintain the water level in a large, leaky bathtub. You have a few taps you can turn on to add water, which are the sources of dust, and you have a drain constantly pulling water out, which are the sinks that destroy dust. The puzzle is that the bathtub, our solar system's dust cloud, is always full. So the taps must be flowing at exactly the same rate as the drain. But when scientists calculate the flow, they find a massive discrepancy. The drain is far too efficient. The primary force draining the dust is something called the pointing Robertson drag. It is a subtle but relentless effect of sunlight itself. As a tiny dust grain orbits the sun, it absorbs sunlight from the front and re-radiates that energy as heat in all directions. This process acts like a constant, gentle brake, stealing the particle's orbital energy. Over thousands of years, this drag causes the dust to spiral slowly, inexorably, inward toward the sun, where it is vaporized. Smaller grains face a different fate. The sheer pressure of sunlight itself can blow them out of the solar system entirely, like cosmic dandelion seeds. And of course, some dust simply collides with planets like Earth, which sweeps up about 40,000 tons of this material every year. These sinks are working constantly, cleaning house. To keep the cloud glowing, we need a tremendous, continuous supply of fresh dust. Our known taps are comets and asteroid collisions, but when astronomers add up all the dust these sources should be producing, the total falls devastatingly short. By some estimates, the observed cloud requires up to 10 times more dust than our best models of comets and asteroids can provide. It is as if you came home to find your bathtub perpetually full, but the taps are only dripping while the drain is wide open. Something, somewhere, must be pouring a colossal amount of fine powder into the inner solar system. But what? The search for that missing source would become one of the most fascinating detective stories in modern astronomy. The search for that missing cosmic dust leads us first to the icy fringes of our solar system. Among the prime suspects is a vast, unseen population of comets, a potential cometary avalanche. The logic is compelling. We know comets are prolific dust factories. Every time one swings close to the sun, its surface erupts, blasting gas and a fine powder of primordial grit into space. But could there be enough of them, hidden in the darkness, to supply the staggering deficit? Astronomers point to two vast reservoirs. The first is the Kuiper Belt, a donut-shaped region beyond Neptune populated by icy worlds and dormant comets. The second is the far more distant Oort cloud, a theoretical spherical shell of icy objects that marks the very edge of the sun's gravitational influence. The theory suggests that a constant, gentle rain of objects is being nudged out of these reservoirs and sent on a long fall toward the inner solar system. The key agents in this delivery system are the giant planets, especially Jupiter. Its immense gravity acts like a cosmic slingshot. An icy body from the Kuiper Belt gets a gravitational kick from Neptune, which sends it on a chaotic path inward. Eventually, Jupiter's gravity can capture it, shortening its orbit and turning it into what is called a Jupiter family comet. These comets have relatively short orbital periods, meaning they make frequent returns to the warm inner regions where they actively shed their dusty coats. Each pass is a miniature blizzard, contributing its share to the zodiacal cloud. The strength of this theory is its elegance. It uses known physics and observed phenomena. We see comets shedding dust. We know the giant planets perturb orbits. Putting these pieces together creates a plausible pipeline for delivering fresh material. Yet the challenge lies in the numbers. To balance the dust budget, this model requires a truly staggering number of small, active comets that we simply have not yet detected. Our telescopes might be missing a hidden population of faint, dusty snowballs, or perhaps the comets we do see are far more productive than we thought. Modeling this chaotic gravitational dance is also incredibly complex, making precise predictions difficult. So while the cometary avalanche remains a compelling and likely contributor, many scientists suspect it cannot be the sole solution to the mystery. The cosmic bathtub is still filling too fast, hinting that another, even more dramatic source must be at work. If comets cannot fully explain the dust, we must turn our investigation inward to the chaotic realm of the asteroid belt. This is suspect number 2, the theory of asteroid collision cascades. Between Mars and Jupiter, millions of rocky bodies orbit in a vast, sprawling disk. It is not the densely packed, clattering junkyard often depicted in films. In reality, the average distance between asteroids is enormous, about 1 million miles. Yet, over billions of years, even rare events add up. When two asteroids do collide, it is rarely a spectacular explosion. More often, it is a grinding, shattering impact that pulverizes rock into fine powder, creating a cloud of debris that slowly disperses. For a long time, astronomers assumed these routine collisions were the steady, primary source of our zodiacal dust. But just as with the comets, the math falls short. The calculated rate of these random crashes simply does not produce enough fine powder to sustain the brilliant glow we see. The bathtub would drain faster than it fills. This forces a more dramatic question. Could a single, cataclysmic event from the distant past be responsible? Imagine a colossal collision, a planetary-scale accident that shattered a Ceres-sized asteroid into billions of fragments. The dust from such an event would flood the inner solar system, creating a temporary but long-lasting spike in the zodiacal cloud. Some of that dust would still be spiraling inward today, tens of millions of years later, providing a lingering echo of that ancient catastrophe. This idea has a certain elegant simplicity. It solves the budget problem with one grand historical event, but it also feels like a special explanation, and science generally prefers ongoing, steady processes to one-off miracles. So perhaps the truth lies in a more subtle and relentless mechanism. This is where a fascinating force called the Yarkovsky effect comes into play. It sounds complex, but the concept is beautifully simple. An asteroid absorbs sunlight on its day side and re-radiates that heat as infrared energy as it rotates. This tiny emission of heat acts like a minuscule thruster. Over millions of years, this gentle thermal nudge can significantly alter an asteroid's orbit, slowly driving it into a resonance zone where Jupiter's gravity can give it a violent kick. The Yarkovsky effect is like a cosmic clockwork, methodically feeding asteroids into chaotic paths where collisions become inevitable. Computer simulations of the belt are mesmerizing to watch. They show not a static field of rocks, but a dynamic, churning system. Asteroids are constantly being nudged, herded by gravity, and gently pushed by sunlight into new orbits. This creates cascades where one major collision generates a family of fragments, which then have a higher probability of colliding with other asteroids, producing more fragments, and so on. It is a slow-motion chain reaction of destruction that could be far more efficient at generating dust than models of random, isolated impacts. So, could asteroid dust alone be sufficient? The latest research suggests it is a major player, especially when you account for these cascading collisions driven by the Yarkovsky effect. But most experts agree it is still not quite enough to close the entire gap in our dust budget. A past giant impact may have given the cloud a foundational layer, a base of ancient dust upon which the steady drizzle from comets and ongoing asteroid collisions continues to fall. The mystery, therefore, deepens. With both prime suspects unable to fully account for the evidence, astronomers were forced to widen the search, to consider sources that were not just hidden but fundamentally invisible. The search for our missing dust leads us to a world much closer to home, but with a surprisingly violent relationship to its own moons. Suspect number 3 in our cosmic investigation is Mars. This is a more recent and startling hypothesis, one that transforms the red planet from a passive bystander into an active, dusty participant in the solar system's ecology. For decades, Mars was seen as just another object within the zodiacal cloud, a place where dust settles, not a place where it originates. New research is challenging that view, suggesting the planet and its strange companions might be spraying a significant stream of fine powder into the space around the Sun. The key lies with Mars's two small, lumpy moons, Phobos and Deimos. These are not smooth spheres like our moon. They are irregular, cratered objects that look remarkably like asteroids because that is almost certainly what they once were. Astronomers believe these are captured asteroids, bodies that wandered too close to Mars long ago and were trapped by its gravity. Their surfaces are not solid rock, but covered in a deep, loose layer of pulverized material called regolith. This regolith is essentially a blanket of cosmic dust and gravel, the result of billions of years of meteoroid impacts, and it is those very impacts that could be solving our mystery. When a small space rock traveling at incredible speeds slams into the surface of Phobos or Deimos, it does not just make a crater. It acts like a cosmic cannon, blasting a plume of debris up and away from the moon's incredibly weak gravity. Because these moons are so small, their gravitational hold is minuscule. It takes very little energy for dust particles to achieve escape velocity. A single, modest impact could eject millions of tons of this fine regolith powder directly into orbit around Mars, and from there, the particles begin their long journey. They get caught in the same solar forces that govern all interplanetary dust, the Poynting Robertson drag and radiation pressure, and slowly join the great flow of the zodiacal cloud. Think of it as a constant, slow-motion sandblasting. Every tiny impact on Phobos and Deimos is like hitting a dusty cushion with a hammer, sending a puff of material out into the solar system. But the moons might not be the only source. Mars itself could be contributing directly through its legendary global dust storms. These are not gentle breezes. They are planet-engulfing monsters with winds lifting fine, rust-colored dust high into the thin Martian atmosphere. Here is where Martian weakness becomes a strength for dust production. Mars has only about 38% of Earth's gravity. Its atmosphere is also extremely thin. This combination means that the uppermost fringes of a major dust storm could be brushing against the very edge of space. For the finest particles, those at the very top of the storm, a single extra jolt of energy, perhaps from solar radiation or a collision with another particle, might be enough to push them over the edge, allowing them to escape Martian gravity entirely. Once free, they become citizens of interplanetary space, another trickle in the stream feeding the zodiacal cloud. This theory fundamentally repositions Mars. It is no longer just a rocky world in the dusty disk. It is an active generator, a planetary system that is processing and exporting material. Its moons act as dusty satellites, being steadily sanded down by impacts, while its own atmosphere occasionally vents its finest powder into the void. When you add this potential Martian output to the contributions from comets and asteroid collisions, the dust budget starts to look a little more balanced. Yet, even with this intriguing new suspect, many scientists feel the case is not fully closed. The calculated rates from Martian moon impacts and dust storms are promising, but pinning down precise numbers is incredibly difficult. We need more data, more direct observation, and that requires turning our investigation from theories and telescopes to something far more direct, sending our own detectives into the dusty cloud itself. Our investigation now stretches to the solar system's magnificent outer giants. Suspect number 4 in the dust mystery is perhaps the most exotic, suggesting that the powder glowing around our Sun might have begun its life in the frigid, geologically active realms of Jupiter and Saturn. Consider the icy moon Enceladus orbiting within Saturn's faint but vast E-ring. This small, bright world is famous for its spectacular cryovolcanic geysers. Fissures at its south pole blast towering plumes of water vapor and fine ice crystals hundreds of miles into space. This is not a gentle mist but a violent, continuous eruption. While much of this icy spray falls back to coat Enceladus in fresh snow, and a significant portion feeds Saturn's diffuse E-ring, a tiny fraction of these particles achieves escape velocity. They break free from Saturn's gravitational grasp entirely, becoming tiny, independent travelers on orbits dictated by the Sun. Now, a particle of ice is not yet a particle of zodiacal dust. But the journey from the outer solar system to the warm inner regions is long and perilous. Over millennia, as these ice grains spiral slowly inward, they are bombarded by solar radiation and micrometeoroids. They sublimate and fracture, gradually grinding down from icy crystals into smaller, rocky or silicate-rich cores, potentially becoming the very kind of fine powder that scatters sunlight so beautifully. This process transforms a geyser's gift into a contributor to the cosmic haze. Saturn's magnificent rings present another potential, though more debated, source. The rings are composed of countless chunks of water ice, ranging from dust-sized grains to house-sized boulders. Constant collisions within the rings generate a steady drizzle of fine material. Some planetary scientists theorize that electromagnetic forces or interactions with Saturn's magnetic field could potentially lift the finest of this dust out of the ring plane and into trajectories that might eventually lead inward. It is a more tenuous pathway, but in the economy of the zodiacal cloud, every trickle counts. Jupiter's system offers its own possibilities. Its moon Io, the most volcanically active body in the solar system, spews sulfur and silicate dust high into the Jovian system. While most is captured by Jupiter's immense gravity, some particles might be ejected through complex gravitational interactions. The concept is staggering in its scale and distance. It proposes that a mote of dust glowing in your evening sky could have begun as an ice crystal in an alien geyser over 1 billion kilometers away. It spent eons on a slow, spiraling pilgrimage toward the Sun, shedding its volatile ices until only a gritty, primordial speck remained. This theory adds a profound layer of complexity and beauty to the origin story. It suggests the zodiacal cloud is not just a local phenomenon, but a solar system-wide repository, a mixing bowl that collects material from every corner of our planetary neighborhood. Yet, for all its poetic appeal, the contribution from the outer giants is likely a minor one. The journey is so long and the forces of destruction so great that only a vanishingly small percentage of this distant material would ever complete the trip to the inner solar system. It is a fascinating tributary, but not the mighty river needed to fill our dusty bathtub. So where does that leave our investigation, with 4 compelling suspects, each contributing a share, but with a budget that stubbornly refuses to balance? To solve this, astronomers knew they needed more than theories. They needed to go there, to send a probe directly into the glowing fog and catch the dust in the act. To truly understand this celestial fog, astronomers had to become cosmic detectives, developing a sophisticated toolkit to study something both everywhere and nowhere at all. Their first and most fundamental instrument is the simple yet powerful ground-based telescope. By carefully measuring the zodiacal light's intensity and its polarization, how the light waves are oriented, they can begin to map the cloud's density and even infer the size and composition of the dust grains. It is like studying a distant fog bank by analyzing the exact quality of the headlight glare shining through it. But Earth's atmosphere is a noisy, glowing curtain itself, filled with its own scattered light and emissions that obscure the faintest details. To see the true nature of the dust, science had to rise above the air. This is where space-based observatories transformed the investigation. Freed from the atmosphere's veil, instruments could peer at the cloud in infrared light, the wavelength of heat. Dust floating in space is warmed by the sun, and it re-radiates that energy as a faint thermal glow. NASA Spitzer Space Telescope and the Japanese Akari satellite were masters of this domain. They did not see reflected sunlight, they saw the dust's own warmth, painting a direct picture of where this material was concentrated and how its temperature changed with distance from the sun. These observations provided a global census, confirming the vast scale of the cloud and sharpening the dust budget problem with hard data. Yet, mapping the globe from afar only tells part of the story. To know what the dust is made of, you need to get your hands on it, or at least get a spacecraft's instruments in its path. Early pioneers in this direct approach were the Pioneer 10 and 11 probes in the 1970s. As they journeyed toward Jupiter and beyond, they carried simple dust detectors, microphones in essence, that listened for the tiny pings of particles striking the spacecraft. Each ping was a data point, a clue to the density of dust in the regions they traveled through. This method is called in situ measurement, and it is the gold standard. It is the difference between studying a snowstorm through a window and stepping outside to catch flakes on your tongue. You learn not just about the storm's outline, but the intricate structure of each individual flake. The dream, then, is to send a dedicated detective right into the heart of the zodiacal cloud, a spacecraft designed not just to pass through, but to actively collect and analyze these motes of cosmic powder. Such a mission could finally answer the fundamental questions: what is this stuff exactly? Is it primarily fluffy comet dust, gritty asteroid fragments, or perhaps a surprising mix with material from Mars or beyond? The data from telescopes and early probes set the stage, outlining the mystery in broad strokes. But to solve it, we need to examine the evidence up close. This pursuit would lead to some of the most ambitious and clever mission concepts ever proposed, ventures that aim to finally catch the solar system's oldest ghost. To solve this mystery, we need a detective willing to fly into the fire. That detective is the Parker Solar Probe, a spacecraft on the most daring mission in the history of solar exploration. Its goal is to touch the sun, diving repeatedly into the star's outer atmosphere, the corona. But on every one of its blistering orbits, Parker must first pass through the very heart of the mystery we have been exploring, the densest region of the zodiacal dust cloud. As it screams toward the sun at nearly 400,000 miles per hour, it is not just observing the dust from a distance, it is plowing directly through it. The spacecraft is equipped with a suite of instruments, but for our dusty investigation, the most critical is its dust impact detection system. Think of it as the most sensitive microphone in the solar system, mounted on the spacecraft's thick, white heat shield. This shield, designed to withstand temperatures hotter than molten steel, becomes a giant target when a speck of zodiacal dust, itself traveling at immense speed, collides with the shield. The impact is catastrophic for the grain. It vaporizes instantly in a tiny flash of plasma. That miniature explosion creates a shock wave that travels through the shield, and the spacecraft's sensors listen for the resulting ping. Each ping is a data point, a direct confirmation of a dust grain's existence and its location relative to the sun. Parker is not catching the dust, it is counting the bullets. The sheer number of these hypervelocity impacts paints a real-time map of dust density where it matters most, in the scorching inner sanctum of our solar system. The early data from this fiery mission has already delivered a stunning surprise. Scientists expected that as Parker dove closer to the sun, the intense heat and radiation pressure would have cleared out the smallest dust grains, creating a relatively dust-free zone near our star. The reality Parker found was the opposite. The probe detected more dust than predicted in these searing regions. The pings did not fade away. They told a story of a persistent, dense population of particles surviving, and perhaps even thriving astonishingly close to the solar furnace. This is a revolutionary clue. It suggests our models of the dust cloud structure are incomplete. Perhaps there is a previously unknown source continuously replenishing dust right near the sun. Or maybe the grains are somehow more resilient, clumping together into fluffier structures that can withstand the hellish environment. Parker's direct evidence forces us to reconsider the entire life cycle of this cosmic powder. Every scorching dive this brave little spacecraft makes is rewriting the textbook, turning theoretical predictions into hard, impact-by-impact facts. It is our best detective on the case, flying through the glowing fog itself and listening to its secrets, one tiny, violent ping at a time. While Parker braves the solar furnace, another mission is preparing for a very different kind of dusty rendezvous. Japan's space agency is gearing up for a launch that promises to be a watershed moment in our investigation. The mission is called Destiny Plus, which stands for Demonstration and Experiment of Space Technology for Interplanetary Voyage with Phaethon Flyby and Dust Science. Its name is a mouthful, but its goal is beautifully precise. This spacecraft is not heading toward the sun. Instead, it is on an intercept course with one of the solar system's most enigmatic objects, the asteroid 3200 Phaethon. This is no ordinary space rock. For years, Phaethon has baffled astronomers by blurring the line between asteroid and comet. It has the orbit of a comet, a wildly elongated path that brings it scorchingly close to the sun, yet it shows no obvious icy coma or gas tail. Instead, it sporadically sheds tiny dust particles, and it is the definitive parent body of the brilliant Geminid meteor shower, one of the year's most reliable celestial displays. Every December, when Earth plows through the debris trail Phaethon has left behind, those particles burn up in our atmosphere as shooting stars. So Phaethon is essentially a rock that acts like a comet, a dusty asteroid that is actively feeding material into the interplanetary medium. Destiny Plus is going straight to the source. After its launch, the spacecraft will embark on a multi-year journey, culminating in a high-speed fly right through Phaethon's faint dust trail. This is where the mission becomes revolutionary. As it zips past, its onboard instruments will not just take pictures. They will perform in situ analysis, directly sampling and analyzing the composition of the dust particles Phaethon is shedding. Think of it as a forensic scientist arriving at a crime scene and being able to chemically analyze the gunpowder residue still hanging in the air. For the first time, we will have a direct, unequivocal sample of dust from a known active solar system body. This data will be a Rosetta Stone for dust science. By knowing exactly what Phaethon's dust is made of, its mineralogy, its structure, its chemical fingerprints, scientists can compare it to the models of both asteroid and comet dust. Does it look like pulverized rock from a catastrophic collision? Or does it have the fluffy, primitive structure of a comet nucleus that has lost all its ice? The answers will provide crucial ground truth, calibrating all our remote observations and tightening the constraints on our dust budget models. Destiny Plus represents a targeted strike in the cosmic detective story. While Parker maps the general population of the dust cloud, Destiny Plus aims to capture and interrogate a specific suspect, one caught in the act of contributing to the mystery. Its findings could finally tell us if bizarre, hybrid objects like Phaethon are major players in sprinkling the inner solar system with their gritty remains, or if they are fascinating oddities in a much larger, still hidden process. The ultimate solution to this mystery may not be a single mission, but a permanent sentinel positioned in the perfect quiet of deep space. That sentinel could be the Lunar Gateway, humanity's first space station in orbit around the Moon. More than just a waypoint for astronauts, the Gateway represents a revolutionary platform for pure science, a stable observatory far removed from the noisy glow of Earth. Our planet's atmosphere is a shimmering, turbulent curtain that distorts and drowns out the faintest cosmic signals. Even our darkest deserts are awash in scattered city light and natural airglow. To see the zodiacal cloud in its true, undisturbed state, we need to step completely outside that luminous bubble. The gateway, circling in the silent, airless void near the moon, offers that pristine vantage point. Imagine mounting a suite of ultra-sensitive instruments on its exterior cameras designed to see the faintest gradients of light, and spectrometers that can dissect that light to reveal the chemical fingerprints of the dust itself. Freed from atmospheric interference, these tools could conduct a long-term, uninterrupted vigil. They would not just take a snapshot, but create a high-fidelity movie of the zodiacal cloud, watching it breathe and change over months and years. They could map the Gegenschein with crystal clarity, measure the exact brightness of the zodiacal band across the entire sky, and detect incredibly subtle variations in the cloud's density and structure. Is there a faint ripple in the dust that corresponds to a recent comet passage? Does the cloud thicken slightly in a specific direction, pointing to a hidden source region in the asteroid belt? These are the nuances that ground-based astronomy struggles to capture, the whispers lost in the atmospheric roar. The gateway's unique orbit also provides a shifting perspective. As it moves around the moon and the moon moves around Earth, it would view the dust cloud from constantly changing angles, allowing for a three-dimensional tomography of this vast structure. We could see its depth and layering in a way never before possible. This continuous, high-precision data would be the gold standard, the baseline against which all other observations, from Parker, from Destiny Plus, from Earth, could be calibrated and understood. It would transform our dusty mystery from a static picture into a dynamic story, revealing the real-time flow of material through our solar system's heart. Positioned at the crossroads of human exploration and fundamental science, the lunar gateway could become the definitive dust observatory, a silent watchtower that finally sees the ghostly glow for what it truly is. This quest to understand our own dusty neighborhood reaches far beyond the borders of our solar system. The faint pyramid of light in your evening sky is not a unique phenomenon. It is a universal signature, a common feature of mature planetary systems. Around distant stars, astronomers detect similar glowing disks of warm dust called exozodiacal clouds. This discovery is thrilling as it hints at the presence of asteroids and comets, the leftover building blocks of planets. But for scientists hunting for a second Earth, this cosmic dust creates a formidable problem. It produces a brilliant, diffuse glare that can completely overwhelm the faint, precious point of light reflected from a small, rocky world orbiting in that star's habitable zone. It is like trying to spot a single, distant firefly hovering right next to a powerful, fog-shrouded searchlight. The glare from the dust obscures the planet. This is why solving the mystery of our own zodiacal cloud is so critical. Our solar system is the only one where we can get up close. By figuring out exactly how much dust is here, where it comes from, and how it behaves, we create a detailed template. We build a reference model of a known, living planetary system with a confirmed dust disk. Astronomers can then apply that model to the blurry data from distant stars. If they see a certain type and brightness of exozodiacal glow, our models can help them estimate how much material is there and, crucially, how much it might interfere with the search for planets. This work directly shapes the design of our future giant observatories, like the planned Habitable Worlds Observatory. That telescope's entire mission will be to directly image and analyze the atmospheres of Earth-like planets around other stars. To succeed, its instruments must include advanced coronagraphs or starshades complex masks designed to block the blinding light of the parent star. But starlight is not the only glare to manage. The design must also account for the diffuse glow of the star's own zodiacal dust disk. Our detective work here at home teaches engineers how to tune their technology, telling them what level of haze to expect and how to filter it out. By deciphering the origins of our own gentle pyramid of light, we are essentially writing the instruction manual for how to see through the fog around other suns. We are learning how to quiet the cosmic background noise, making the soft whisper of an alien world suddenly audible. The solution to this ancient mystery, therefore, becomes a key that unlocks doors across the galaxy, turning a local puzzle into a universal guide for finding new homes among the stars. That beautiful, ethereal glow is not just a scientific puzzle, it is a navigational hazard. For every spacecraft we send beyond Earth, the zodiacal cloud is a permanent, invisible minefield. Each of those trillions of dust grains, many smaller than a grain of sand, is traveling at staggering speeds, orbiting the Sun at tens of thousands of miles per hour. When a spacecraft moving in the opposite direction collides with one, the relative velocity can approach 100,000 miles per hour. At that speed, even a microscopic speck carries the kinetic punch of a rifle bullet. These hypervelocity impacts are a constant, erosive threat known as micrometeoroid damage. They can pit and cloud sensitive optics like telescope lenses and camera windows, gradually sandblasting them opaque over a long mission. They can degrade the performance of solar panels, slowly chipping away at their power-generating surface. And in a worst-case scenario, a slightly larger grain, perhaps the size of a salt crystal, could puncture a critical component, a fuel line, or even the pressurized hull of a crew capsule. This is not science fiction, it is a routine engineering challenge. Every mission to the Moon, to Mars, or to the asteroids must have its shielding and systems designed with this dusty environment in mind. The thickness of a spacecraft's Whipple shield, a protective bumper designed to vaporize incoming particles before they hit the main hull, is calculated based on predictions of how much dust it will encounter along its path. And that is where the mystery of the zodiacal cloud becomes a matter of practical safety. To design a shield, you need to know exactly what you are shielding against. If our dust budget is wrong, if there is 10 times more material out there than we think, or if it is concentrated in unexpected regions, then our spacecraft could be underprotected. A mission to Mars, which must travel through the thickest part of the dust disk, relies on accurate maps of this cosmic fog. Solving the origin and distribution of the zodiacal light is, therefore, directly linked to the safety of astronauts and the longevity of billion-dollar satellites. But the hazard might be more than just physical. There is another, more subtle interaction to consider. As these fine dust grains float in space, they are constantly bathed in the sun's intense ultraviolet light and the flood of charged particles known as the solar wind. This can strip electrons from the dust, leaving the particles themselves electrically charged. Suddenly, this passive cloud becomes an active component of the space environment. Charged dust does not just drift, it can be pushed and pulled by magnetic fields embedded in the solar wind. It could potentially influence the very structure of the heliosphere, the vast bubble of solar wind that surrounds our planetary system. On a smaller scale, this charged, abrasive dust sticking to sensitive electronics or solar arrays could cause unexpected discharges or short circuits. For future outposts on the Moon or Mars, where regolith dust is already a major headache, understanding how interplanetary dust behaves when electrified will be crucial. The gentle pyramid of light, then, represents more than ancient history. It is a real-time map of a navigational and environmental condition, a permanent feature of the space weather forecast. To become a truly spacefaring civilization, we must learn to read its subtle variations, to see the hazard within the beauty, and to navigate the dusty sea between the worlds. This cosmic detective story still has room for a crucial partner, you. While billion-dollar probes dive toward the sun and space telescopes map the infrared sky, some of the most valuable data comes from a far more humble source, dedicated skywatchers standing on a dark hill with a camera. The study of the zodiacal light is a perfect frontier for citizen science, where amateur astronomers can contribute observations that are genuinely precious to the larger investigation. In an era of overwhelming light pollution, A clear, documented sighting of this subtle glow from a pristine location is a scientific data point in itself. It helps researchers monitor the baseline brightness of our night sky, tracking how atmospheric transparency and the encroaching glow of human civilization affect our view of the cosmos. Your photograph could become part of a global dataset. Capturing this ghostly pyramid is a rewarding challenge that requires patience and the right technique. First, you need to escape. Find the darkest sky you can, far from city lights, on a moonless night with exceptionally clear, dry air. The best windows are in early spring after evening twilight fades, or in late autumn before dawn begins to break. Your essential tool is a camera capable of manual settings, mounted on a sturdy tripod. Use a wide-angle lens to frame the vast conical shape rising from the horizon. Set a wide aperture to gather as much light as possible, and use a long exposure, often 30 seconds or more, to let that faint glow accumulate on the sensor. You will likely need to take many such exposures. The real magic happens afterward in processing. Using free software, you stack those dozens of individual images together. This technique averages out the random noise in each shot, gradually revealing the smooth, ethereal structure of the light, separating the true signal from the background murk. By sharing your successful images and the details of your location and conditions with organizations like the International Dark Sky Association or specific university research projects tracking skyglow, you do more than just create art. You become a sentinel. You help scientists build a living map of atmospheric clarity and document the actual visibility of our solar system's dusty skeleton. Each clear observation is a timestamp, a note in a long-term record that shows how this permanent celestial structure appears through the ever-changing veil of our own planet's atmosphere. In doing so, you join a lineage of observers stretching back centuries, using modern tools to witness an ancient mystery and add your piece to the puzzle of where all that beautiful, mysterious dust comes from. Even the most beautiful cosmic structures have their strange, unexplained quirks. Throughout history, alongside the standard descriptions of a soft, featureless cone, there are scattered but compelling reports of something different. Mariners and astronomers in centuries past occasionally wrote of the zodiacal light appearing not as a gentle glow, but as a brilliant, almost structured pillar, or displaying unusual knots and ripples in its light. These were not common sightings, and they were often met with skepticism. Today, we have a likely culprit for these historical anomalies: transient, catastrophic events. Picture a major comet, perhaps a kilometer across, suffering a sudden breakup as it rounds the sun. Such an event would not just release dust, it would unleash a blizzard, a localized storm of fresh, reflective particles injected directly into the interplanetary flow. For a few years, that dense cloud of debris would orbit the sun, spreading out along the comet's path. If Earth passed through that enriched stream, the zodiacal light could temporarily become shockingly vivid and detailed, a ghostly monument to a distant shattering. These events are rare, but they remind us that the dust cloud is not a static painting. It is a dynamic fluid, occasionally stirred by violent inputs that briefly illuminate its hidden currents. Beyond these transient spikes, theory suggests there might be permanent, hidden structures within the haze. Just as Saturn's gravity sculpts its magnificent rings, the planets closer to the Sun may be shaping the dust in subtler ways. Orbital dynamics predict the existence of what are called gravitational resonances. These are stable zones where the orbital period of a dust particle syncs up perfectly with a planet's orbit. Think of it like pushing a child on a swing. If you push at just the right moment in the swing's arc, you add energy efficiently. A planet's gravity can act similarly, giving tiny, consistent nudges to dust grains that happen to orbit at specific distances. The result could be faint, concentrated rings of dust sharing the orbit of Earth or Venus but spread out along the path. They would be incredibly diffuse, nothing like Saturn's brilliant ice rings, but they would represent a slight thickening, a ghostly echo of the planet's path traced in ancient powder. Our current telescopes struggle to see such fine detail within the overall glow, but the mathematics strongly suggests these planetary dust rings should be there, woven into the fabric of the zodiacal cloud. This leads to a fundamental and unresolved debate about the very texture of the dust cloud. Is it truly a smooth, homogeneous fog like milk stirred into coffee? Or is it, upon closer inspection, a tapestry of countless faint streams and clumps, each the fading trail of some individual comet or asteroid family? The difference is critical. A smooth distribution points to a well-mixed cloud where the dust from countless sources has been churned together over millions of years by gravitational interactions and solar forces. It suggests an old, settled system. A clumpy distribution, however, would be a sign of youth and ongoing activity. It would mean we could potentially trace ribbons of dust back to their parent bodies, identifying specific comets or asteroid collisions as major contributors that have not yet had their output smoothed into the background. Our current data hints at both. The overall glow is smooth, but sensitive probes like Parker might be detecting the statistical signature of denser filaments. Resolving this is like trying to determine if a distant forest is one solid mass of green or a collection of individual trees. We see the color but not the details. This ambiguity is what keeps the mystery so electrically alive. Every new observation, every daring mission, is an attempt to sharpen our vision, to see whether the solar system's oldest glow is the serene face of a settled antiquity or the shimmering, dynamic skin of a system still being actively built, one dusty grain at a time. What if our solar system's dust is not all homegrown? Among the most captivating theories is the possibility of an interstellar contribution. This idea suggests that a tiny fraction of the powder creating our pyramid of light might have begun its life around another star entirely. Our Sun, with all its planets and dust, is not stationary. It sails through the galaxy at over 400,000 miles per hour. On this grand voyage, it is constantly plowing through what astronomers call the local interstellar cloud, a tenuous but real region of gas and dust that fills the space between stars. Just as a car driving through a light snowfall collects flakes on its windshield, our solar system might be sweeping up some of this galactic material. The process is gentle and gravitational. A microscopic grain of interstellar dust drifting near the edge of our Sun's sphere of influence could be slowed ever so slightly by the solar wind or nudged by a passing planet's gravity. If it loses enough speed, it becomes captured, falling into orbit around our Sun and joining the great flow of the zodiacal cloud. It is a cosmic immigration story on the smallest scale. The discovery of 2 confirmed interstellar visitors in recent years makes this idea far less speculative. In 2017, the strange, elongated object named Oumuamua tumbled through our inner solar system. Then, in 2019, comet Borisov arrived, looking remarkably like a comet from our own system, but on a path that declared its extrastellar origin. These were not dust grains, but sizable objects, proving that material from other star systems does indeed cross our threshold. If such large visitors exist, then a steady, invisible drizzle of their microscopic cousins seems almost inevitable. While current models suggest this interstellar dust is a very minor contributor to the overall zodiacal cloud, perhaps only 1% or less, its potential presence is transformative. It means that the gentle glow in our springtime evening sky could contain, within its countless trillions of particles, a handful of genuine alien artifacts. A few motes of that ethereal light might be made of stardust forged in a supernova explosion that occurred light years away, around a star we may never even identify. They are silent ambassadors from the galactic community, their journey measured in millions of years, their final resting place the luminous fog of our own solar system. This theory adds a profound galactic dimension to our dusty puzzle. It suggests the zodiacal cloud is not merely a record of our solar system's history, but also a collector's cabinet for samples from across the Milky Way. That faint pyramid is more than a scientific puzzle, it is a cosmic memorial. Every photon of that gentle light has bounced off a fragment of a world that never was. It is the scattered ash of asteroids shattered in ancient collisions, the last glittering remnants of comets that spent their substance in a final, glorious blaze near the sun. This ethereal fog is both a celestial cemetery and a perpetual construction site. It holds the ruins of failed planets and the raw materials for worlds yet to come, a continuous cycle of destruction and potential painted across the sky. For millennia, this elusive glow has stirred something deeper than curiosity in the human spirit. In art and poetry, it often appears not as a physical phenomenon, but as a symbol of the intangible, a bridge to the divine, a hint of a higher realm just beyond perception. Its transient beauty, visible only under perfect conditions, made it a metaphor for fleeting truth or spiritual awakening, a light that could be witnessed but never grasped. This cultural echo reminds us that our drive to solve this mystery is not merely technical. It is a fundamental human yearning to comprehend our origins and our context. We are not just analyzing dust, we are attempting to read our own origin story, a history written not in stone, but in countless microscopic specks adrift between the planets. Each grain is a page from a chaotic past, telling of violent impacts in the asteroid belt, of icy wanderers disintegrating near the sun, and perhaps of materials born around other stars. To decipher this scattered archive is to understand what our solar system is made of, and by extension, what we ourselves are made of. Solving the mystery of the zodiacal light means learning to translate the autobiography of our celestial neighborhood, written in a language of scattered light and silent, ancient dust. The ultimate sample would be a vial of this cosmic powder, returned safely to a laboratory on Earth. While missions like Destiny Plus will analyze dust on the fly, the scientific Holy Grail is a sample return mission dedicated to the zodiacal cloud itself. Imagine a spacecraft equipped with a specialized collector, perhaps a tray of ultra-pure aerogel, a substance so light and porous it looks like solidified smoke. This probe would spend months or even years in a stable orbit within the densest part of the dust disk, its collector open like a cosmic butterfly net. The challenge is not just catching the dust, but catching it gently. These particles strike at speeds exceeding 10 kilometers per second. Upon impact, they would normally vaporize instantly, their chemistry lost in a flash of plasma. To preserve them, engineers are dreaming up ingenious systems. One concept involves an electrostatic field that gently slows incoming charged particles just before contact, like a soft cushion of energy. Another idea uses a rotating collector that moves in the same direction as the dust stream, dramatically reducing the relative impact speed. The goal is to bring back these pristine grains, frozen in time, for the most powerful microscopes and mass spectrometers on our planet to scrutinize. In a lab, we could perform analyses impossible from a distance. We could slice a grain thinner than a human hair to see its crystalline structure, measure exact isotopic ratios that act as a birth certificate for its origin, and search for complex organic molecules. Such a mission would definitively answer the core question, what is this stuff made of, and by extension, where did it come from? It would turn the glowing mystery into a tangible, hold-in-your-hand reality. Looking even further ahead, the technology shifts from passive collection to active management. For future giant space telescopes, like the proposed Habitable Worlds Observatory, the diffuse glare of the zodiacal cloud is a major obstacle. What if we could push that dust aside? This ventures into the realm of visionary engineering, but the principles are grounded in physics. Since many of these particles carry a slight electric charge, one could imagine deploying a network of small satellites around a telescope. These satellites would generate precisely tuned electromagnetic fields, creating a kind of protective bubble that gently deflects charged dust grains away from the instrument's sensitive line of sight. It would be a dynamic, invisible shield, constantly adjusting to clear a temporary window in the cosmic fog. A more speculative concept involves using directed energy, a broad, diffuse laser beam, not to vaporize the dust but to exert gentle radiation pressure. By shining this light against the cloud from the spacecraft, it could theoretically nudge the finest particles away over time, creating a clearer path for observations. This is not about destroying the dust, but about sculpting our local environment, creating a temporary clearing in the interplanetary haze to see the universe beyond with unprecedented clarity. Such ideas transform our relationship with the solar system from one of mere observation to one of subtle interaction. They propose a future where we don't just navigate through the dusty sea between worlds, but learn to part its waves for a better view. This long-term vision redefines the zodiacal cloud. It is no longer just a beautiful mystery or a navigational hazard, but a potential medium to be understood and one day gently manipulated. The journey from wondering about a faint glow on the horizon to contemplating how to shape that glow for our scientific benefit captures the profound arc of human curiosity. It asks a bold final question: as we become a true spacefaring civilization, will we learn to read not just the stories written in the dust, but also to write our own subtle signature upon it? The glowing dust between planets may one day be more than a scientific curiosity. It could become a ledger in a cosmic economy. As humanity's gaze shifts from mere exploration to utilization, the very particles that create the zodiacal light enter a new kind of spotlight. Could we ever harvest this material? The practical challenges are almost unimaginable. The dust is fantastically sparse, with only a few grains per cubic kilometer of space, and each one is a hypervelocity bullet traveling at tens of thousands of miles per hour. Designing a collector that could gently capture these motes without being sandblasted into oblivion would require technology we can barely conceive of today. The energy cost of chasing down and corralling this microscopic, diffuse resource would almost certainly outweigh any potential gain. For the foreseeable future, the zodiacal cloud remains a scientific target, not a commercial one. Yet, its true economic value lies not in direct collection, but in the profound intelligence it provides. Every speck of this dust is a free sample, a tiny ambassador from the asteroids and comets that are the real targets of the future space economy. This ethereal fog is in essence a pre-processed survey. It has already done the hard work for us, grinding down asteroid material into a fine powder and delivering it throughout the inner solar system, right into our observational path. By analyzing the composition of this dust, whether from missions like Destiny Plus or from telescopes, we are conducting a massive, passive prospecting campaign. We learn what minerals are out there, how much precious metal might be locked within the rock, and the structural integrity of the parent bodies. A grain of zodiacal dust that tests high in platinum group metals or rare earth elements is a glowing signpost pointing back to the asteroid belt and saying, "Look here." The knowledge we gain from solving this ancient mystery directly informs the business plans of asteroid mining ventures. It helps them assess which asteroids are most valuable, which are most accessible, and what processing techniques will be needed to extract their resources. So while we may never sweep up the pyramid of light itself, understanding it illuminates the path to the real treasure, turning a beautiful cosmic mystery into a practical guidebook for the next giant leap in our economic future. The most elegant answer to this cosmic mystery is not a single source but a grand collaboration. After centuries of investigation, from medieval astronomers to daring solar probes, the evidence points toward a unified theory. The zodiacal cloud is not the product of one dominant process, but a complex, ever-changing blend of all the suspects we have met on this journey. It is a celestial soup, and every spoonful contains ingredients from across the solar system. The brilliant dust from short-period comets, the gritty powder from asteroid collisions and cascades, the fine regolith sandblasted from the moons of Mars, and even a whisper of material from the icy fountains of the outer moons. All of it spirals together in the sun's gentle gravity, mixing into the permanent glowing fog we see from Earth. The real mystery, then, is not what but how much. The scientific challenge has shifted. We are no longer searching for a lone culprit to arrest. Instead, we are forensic accountants tasked with determining the precise mix. What percentage of the glow comes from comets versus asteroids? Is the contribution from Phobos and Deimos a steady trickle or a major river? Does a single, ancient catastrophic collision still account for a foundational layer of the dust? These are the questions that drive missions like Destiny Plus and the analysis of Parker Solar Probe data. Each new observation adds a data point, helping us refine the recipe. This is how science often works at the frontier. Progress is not always a dramatic eureka, a moment that reveals a single, shocking truth. More often, it is a patient process of elimination and refinement. We rule out what cannot be true, we tighten the error bars on our estimates, and we gradually piece together a mosaic of truth from many small, hard-won tiles of evidence. The zodiacal light mystery is a perfect example of this beautiful, collaborative detective work. It reminds us that our solar system is not a collection of isolated objects, but a deeply interconnected ecosystem. A comet's death near the Sun, an asteroid's collision in the belt, a meteoroid's impact on a tiny moon, these events in distant corners are all connected by this faint, luminous bridge. The dust they produce becomes part of a shared reservoir, a common environment that all the inner planets swim through. Solving the budget is about understanding the economy of this entire system, tracing how material flows from its violent origins to its quiet, glowing rest in the inner solar system. So the next time you find yourself under a truly dark sky, and you glimpse that faint pyramid rising from the horizon, see it for what it truly is. You are not looking at one mystery, but at the merged light of 100 million stories. You are seeing the combined glow of forgotten comets, long-vanished asteroids, and the silent, sandy erosion of distant moons. It is the autobiography of our solar system, written in a language of scattered sunlight, and we are only now learning how to read it. This cosmic dust is a record of our own story, and reading it changes how we see our place in the universe. Understanding the zodiacal cloud is not an abstract academic exercise, it is a fundamental act of mapping our home. That faint glow is a dynamic archive holding clues to the violent construction of our planetary system, the steady rain of material that still falls today, and even the potential ingredients for life itself that were delivered to the young Earth. By solving its origins, we are essentially writing the first accurate history of our solar system, one based not on theory alone, but on the physical evidence floating right in front of us. This work has immediate practical stakes. For the safety of every astronaut who will venture to the Moon or Mars, an accurate map of this dusty environment is as crucial as a weather forecast. Knowing the density and size of particles along their route informs the design of spacecraft shielding, protecting lives and billion-dollar missions from the silent sandblasting of interplanetary space. On a grander scale, the solution to this local mystery is the key that unlocks our search for life beyond Earth. Our sun's zodiacal glow is the baseline, the example we know best. When astronomers point their most powerful future telescopes at distant stars, the haze they see around those suns, the exozodiacal light, will either be a beacon hinting at asteroid belts and comets, or a blinding fog obscuring small, rocky planets. Our ability to distinguish between those two possibilities, to see through the cosmic glare to spot another pale blue dot, depends entirely on the hard-won knowledge we are gathering right here, right now. This long-standing puzzle is a powerful testament to human curiosity. For centuries, a phenomenon visible to anyone under a pristine sky has resisted full explanation, challenging some of our greatest scientific minds. It proves that profound and beautiful mysteries are not confined to the distant edges of the cosmos. They linger in our own celestial neighborhood, waiting patiently for the moment when our technology, our patience, and our wonder finally align. That pyramid of light is an invitation. It asks us to look up, to question what we see, and to remember that the universe is always more intricate and interconnected than it appears. The next chapter of this story is being written by the probes diving toward the sun, the telescopes watching from lunar orbit, and the observers capturing its glow from a dark hillside. It is a story that belongs to anyone who has ever gazed at a starry sky and felt the pull of a question without an answer. So the story of the zodiacal light is a journey from a simple, beautiful sight to a profound cosmic detective hunt. We began with that ghostly pyramid rising from a dark horizon, a whisper of light witnessed for centuries. We followed the clues inward, discovering it was the glow of a vast sea of interplanetary dust, a permanent fog through which Earth swims. The mystery deepened when we tried to balance the books, finding that the known sources of this dust, comets, asteroid collisions, even the moons of Mars, could not fully account for the brilliant, persistent cloud we observe. The bathtub of our solar system stays full, but the taps seem to drip while the drain is wide open. This puzzle has driven some of the most daring missions in space exploration. Right now, the Parker Solar Probe is diving through the heart of this dust, counting hypervelocity impacts as it braves the sun's fury. Soon, the Destiny Plus mission will fly through the dust stream of asteroid Phaethon, directly sampling the output of a known supplier. And future platforms like the Lunar Gateway promise to become pristine observatories, watching the clouds' every subtle change from the silent void. We stand on the brink of revolutionary answers. The combined data from these ventures will finally allow us to weigh the contributions, to write the precise recipe for our solar system's dusty haze. It will tell us if a cataclysmic event from the deep past still echoes in the glow, or if a steady, hidden rain from the outer solar system is the key. This is not just about dust, it is about writing the true history of our celestial neighborhood and learning to navigate its hidden currents safely. But this story does not belong only to scientists and spacecraft. It belongs to anyone who looks up. The next clear, moonless night in early spring or late autumn, find the darkest sky you can. Let your eyes adjust to the profound blackness and scan the horizon where the sun has recently set or is about to rise. Search for that faint, tapering cone of light. If you see it, you are not just observing a scientific phenomenon. You are witnessing the merged glow of 100 million stories, the illuminated dust of comets, asteroids, and worlds. You are seeing the very mystery we have explored with your own eyes. When you do, you become part of this centuries-long quest. Share what you see. Tell us in the comments if you have ever spotted the zodiacal light, or if you plan to try. Your observation connects you to astronomers past and present, and to follow this story to its conclusion, subscribe for updates. We will be here to share the groundbreaking discoveries from Parker, from Destiny Plus, and from the next generation of explorers. The solution to this ancient, beautiful glow is closer than it has ever been. We are finally learning to read the autobiography of our solar system, written in scattered sunlight and silent dust, and the next chapter is about to be revealed.